Hey guys, welcome back to Cyber Platter. This is part one of networking interview question and answer series. I will link the other videos related to networking interviews in the description box. Let's go to our first question. What is a computer network? It is a collection of interconnected computers and devices that can communicate with each other to share, say, resources, information, and services. These interconnected devices can be physically connected via cables or wirelessly connected through radio waves, forming a network that allows data and information to be transmitted and exchanged between them. Let's see some of the key components and concepts of a computer network. First one is nodes. These are the individual devices connected to the network, such as computers, servers, routers, switches, and printers. Then we have links. These are physical or logical connections that allow data flow between nodes. Links can be wired like Ethernet cables or wireless like Wi-Fi. Next is topology. This is arrangement or layout of nodes and links in a network defining how they are connected. Let's see some common topologies. So first one is point to point. This is how it is connected. Then we have something called as bus. The connection looks like this. Then there is ring, like the name suggests, the devices are connected in this way. Then there is star. There's one central device that is connected to the other devices in star topology. And then there is mesh. So mesh can be connected like this, it can be anything mesh. And then there is tree, like the name suggests, it is a tree structure. So these are some of the common topologies. Going back to the components of computer network, we have protocols. These are rules and standards that govern how data is transmitted, received, and intercepted in the network. Examples include TCP/IP, that is Transmission Control Protocol, and IP Protocol. Another example is HTTP, that is Hypertext Transfer Protocol. Another key component is IP addresses. These are unique numerical addresses assigned to each device on the network to identify and locate them. Then there is data transmission. This is the process of sending and receiving data packets between devices, ensuring that data is properly formatted, transmitted, and received. So computer networks serve various purposes, including sharing files and resources, providing internet access, enabling communication through email and messaging, supporting remote access, and facilitating collaborative work among users and devices. They are a fundamental part of modern computing, enabling connectivity and the exchange of information on a global scale. Let's go to the next question. Define the OSI model and its layers. OSI stands for Open Systems Interconnection Model. It is a conceptual framework used to understand and standardize the functions of a network or telecommunication system. It divides the network communication process into 7 distinct layers, each responsible for specific tasks and functions. These layers help ensure that different hardware and software components can work together seamlessly, regardless of the underlying technologies. Now let's see the 7 layers of OSI model. Layer 1 is at the bottom and layer 7 is the topmost layer. So we will start with layer 1, that is the bottom layer. It is the physical layer. This deals with the physical medium of communication such as cables, connectors, and electrical signals. It defines the physical characteristics of the transmission medium, including voltage level, signal timing, and data encoding methods. Devices in this layer include network cables and other physical infrastructure components. The next layer is data link layer, that is layer 2. This focuses on data framing, error detection, and MAC, that is media access control. It ensures that data is transmitted reliably across the physical layer. This layer also manages access to the physical medium, handles error detection, and retransmits data if necessary. Ethernet switches operate at this layer. Then the third layer is the network layer. So the network layer is responsible for routing packets from the source to the destination across multiple networks. So it deals with logical addressing, routing, and packet forwarding. Routers operate at this layer, and IP addresses are used to identify devices on different networks. Then the next layer is the transport layer, which is the fourth layer in the OSI model. This ensures end-to-end communication, reliability, and data flow control. It manages the segmentation and reassembly of data into smaller packets if needed, as well as error detection and correction. The most common protocols at this layer are TCP, that is Transmission Control Protocol, and UDP, User Datagram Control. And the next layer in OSI model is the session layer, that is the fifth layer. This layer manages and establishes communication sessions between devices. It handles session initiation, maintenance, and termination. This layer is responsible for managing dialogue control. This layer is responsible for managing dialogue control and synchronization between applications. Then the next layer is presentation layer, which is the sixth layer. This layer deals with data translation, encryption, and compression. It ensures that data is presented in a format that the application layer can understand. This may involve data encryption, data compression, or character encoding or decoding. Next is the application layer, which is the seventh layer, topmost one. This interacts directly with the end user applications and services. It provides a user interface and services for applications, allowing them to interact with the network. Protocols like HTTP, FTP, SMTP, and DNS operate at the application layer. So the OSI model serves as a reference framework to help networking professionals understand and troubleshoot network issues by identifying the specific layer where a problem may occur. It also provides foundation for the development and implementation of networking protocols and technologies. The next question is, what is TCP IP model and how is it related to the OSI model? Like I mentioned before, TCP IP stands for Transmission Control Protocol and Internet Protocol. Is a suite of networking protocols used for communication on the internet and within private networks. It is the foundation of modern internet communication and is responsible for routing data packets between devices, ensuring data integrity, and providing end-to-end communication. Let's see how now TCP/IP model relates to the OSI model. You should remember that TCP/IP is not a strict match for the OSI model 7 layers. However, its functionality can be loosely mapped to the OSI layers. So let's go back to the OSI model. So TCP/IP has only 4 layers: network access layer, internet layer, transport layer, and application layer. First is the network access layer. In TCP/IP, this layer combines the functionalities from both physical and data link layers of the OSI model. So it deals with network hardware, device addressing, that is MAC addresses for example, and data link protocols, for example Ethernet. Next is the internet layer, which corresponds to the network layer of the OSI model. It handles logical addressing like IP addresses, routing, and packet forwarding. Then there is transport layer, which corresponds to the transport layer of the OSI model. It includes protocols like TCP and UDP, which manages end-to-end communication, error detection, and data flow control. Then there is application layer. This aligns with the OSI session layer, presentation layer, and application layer. It includes various application level protocols and services such as HTTP, FTP, SMTP, and DNS. So that's how TCP IP and OSI model are connected. So TCP IP is often referred to as a simplified or condensed version of the OSI model because it combines some of the OSI layers for practicality. It is tailored for the specific requirements of internet communication. While the OSI model is a conceptual framework, TCP IP is the practical set of protocols used in real world networking, especially on the internet. It provides the actual mechanisms for data transmissions and network communication. So, in summary, TCP IP is a suite of networking protocols that serves as the foundation for internet communication. While it doesn't directly align with the OSI model's layers, it provides similar functionalities and is widely used in practice for data transmission and network communication. The OSI model is a conceptual framework that helps in understanding networking concepts and serves as a reference model for network design and troubleshooting. Let's go to the next question. Explain the difference between a hub, switch, and a router. Hubs, switches, and routers are three distinct networking devices with different roles and functionalities in a network. Let's see the differences between them. First, we'll talk about hub. Hub is the simplest and most basic networking device. It operates at the physical layer of the OSI model, that is layer 1. When a hub receives data on one of the ports, it broadcasts the data out to all other ports regardless of the destination. It does not make decisions about where to send data. Hubs create a single collision domain, meaning that when two devices transmit data simultaneously, a collision occurs and both devices must retransmit their data. Hubs are inefficient because they flood the network with unnecessary traffic, leading to congestion and slower performance. Hubs are rarely used in modern networks due to their inefficiency and inability to handle today's data rates. They have been largely replaced by switches. Now let's discuss about switches. A switch is a more advanced networking device that operates at the data link layer, that is the layer 2 of the OSI model. Switches use MAC addresses to determine the destination of data packets. When a switch receives data, it forwards the data only to the port where the destination device is connected, reducing unnecessary traffic. Switches create separate collision domains for each port. This minimizes collisions and improves network efficiency. Switches are highly efficient and provide faster data transfer rates compared to hubs. They are suitable for modern networks. Switches are commonly used in LANs, that is local area networks. This is to connect multiple devices within a single network segmentation. Next is routers. A router is a networking device that operates at the network layer, that is layer 3 of the OSI model. Routers are responsible for routing data between different networks or subnets. They use logical addressing, IP addresses, to determine the appropriate path for data packets to reach their destination. Routers make decisions based on network addressing and routing tables. They can connect multiple networks and can make intelligent routing decisions. Routers isolate broadcast domains, which means that they prevent broadcast traffic from one network segment from affecting others. This enhances network security and efficiency. Routers are used to connect multiple LANs or to connect LANs to the internet. They play a crucial role in interconnecting different networks. So, in summary, hubs are basic devices that broadcast data to all connected devices, creating a single collision domain. They are outdated and inefficient. Switches are more advanced devices that use MAC addresses to forward data only to the specific port where the destination device is located. They create separate collision domains and are widely used in LANs. Routers are network devices that operate at the network layer and are used for routing data between different networks. They isolate broadcast domains and are essential for interconnecting networks, including connecting LANs to the internet. Let's move on to the next question. What is the purpose of ARP? ARP stands for Address Resolution Protocol. ARP is a fundamental protocol in computer networking, specifically at the data link that is layer 2 of the OSI model. Its primary purpose is to resolve or map an IP address to the corresponding physical MAC address, that is media access control, on a local network segment. ARP plays a crucial role in enabling communication between devices on the same local network or subnet. Let's see the key purposes one by one now. First one, like we discussed, IP to MAC address resolution. When a device in a local network wants to communicate with another device using its IP address, it first needs to determine the corresponding MAC address of the target device. ARP is used to resolve this mapping. Okay. Next key purpose is the broadcast mechanism. ARP operates using broadcast messages. When a device needs to find the MAC address associated with a particular IP address, it sends an ARP request packet as a broadcast message to all devices within the local network segment. Next one is request response process. First, we'll talk about ARP request. The ARP request packet contains the IP address of the target device that the sender wants to communicate with. It essentially asks for who has this IP address. The device with the requested IP address responds with an ARP reply packet that includes its MAC address. The reply packet essentially says, I have that IP and here is my MAC address. So the next point is caching ARP entries. To avoid sending ARP requests for every communication, devices maintain an ARP cache or ARP table. This cache stores the IP to MAC address mappings that have been recently resolved. When a device needs to communicate with another device on the same local network, it checks its ARP cache first. If the mapping is found, it can use the cached MAC address for communication. Next one is the dynamic nature. ARP mappings are not static and can change over time, especially on dynamic networks where devices join or leave. ARP entries in the cache may expire and devices may need to refresh them by sending new ARP requests. So, in summary, the ARP is used to map IP addresses to MAC addresses within a local network or subnet. It allows devices on the same network to communicate with each other by resolving the necessary layer 2 addressing information, that is the MAC address. ARP operates through a request response mechanism and devices maintain ARP caches to improve efficiency in resolving address mappings. Let's move on to the next question. Explain the concept of a MAC address. MAC is short for Media Access Control. It is a unique identifier assigned to a network interface for communication on a physical network. Network interfaces such as network adapters or network interface cards. It is a hardware address. It operates at the data link layer. MAC addresses are essential for the proper functioning of the Ethernet and other data link layer technologies. Let's see some of the key aspects of MAC addresses. First thing is uniqueness. Like I mentioned before, every network interface in the world should have a globally unique MAC address. This uniqueness is typically ensured by manufacturers who assign a unique MAC address to each network interface they produce. The uniqueness of MAC addresses is crucial to prevent address conflicts on a network. Next is 48-bit address. A standard MAC address is 48 bits, that is 6 bytes in length. This is often represented as 12 hexadecimal characters. For example, it might look like 001A or 2B, 2C, 3C, 4D, 5E. This is an example of a MAC address. The first 3 bytes or 24 bits typically identify the manufacturer, known as the originally unique identifier or OUI, and the remaining 24 bits or 3 bytes represent the unique identifier assigned by the manufacturer to that specific network interface. Next characteristic of MAC, locally administered address. In addition to globally unique addresses, network administrators can assign locally administered MAC addresses to devices. These addresses are not registered with the manufacturer and can be useful for specific network configurations or testing purposes. Next one, role and data link layer. MAC addresses are used by network devices such as switches and network interface cards to determine how to forward data frames within a local network segment. When a device wants to send data to another device within the same local network, it uses the MAC address of the destination device to ensure that the data reaches the correct destination. Next one, like we mentioned, layer 2 addressing. MAC addresses are an example of layer 2 addressing. They are used for communication within the same network segment and play a vital role in the framing of Ethernet packets. Next one, not routable. Unlike IP addresses, which are used for routing data across different networks, MAC addresses are not routable. They are only relevant within the confines of a local network segment. Then another aspect of MAC is ARP, that is, like we discussed, address resolution protocol. This is used to map an IP address to its corresponding MAC address on the local network. This mapping is crucial for devices to communicate within the same network segment. So in summary, a MAC address is a unique hardware address assigned to network interfaces for communication within a local network segment. It plays a fundamental role in the data link layer of networking protocols like Ethernet and is essential for devices to correctly identify and communicate with each other on a local network. Let's move on to the next question. Describe the function of ICMP. ICMP stands for Internet Control Message Protocol. This is an essential network protocol in the TCP/IP suite of protocols. Its primary function is to facilitate the exchange of control and error messages between network devices. This is to assist in network troubleshooting and management. ICMP is often used by network administrators and devices like routers and network utilities to communicate network related information. Let's see some of the key functions of ICMP. First one is error reporting. ICMP is responsible for reporting various types of errors that occur during network communication. For example, if a router cannot forward an IP packet due to network congestion or other issues, it may generate an ICMP error message to inform the source device about the problem. Next is network diagnostics. ICMP provides network diagnostic tools with essential information to help diagnose network issues. For example, the ping command uses ICMP echo requests and replies to check network connectivity and measure round trip time. Next is router discovery and advertisement. ICMP includes router discovery and router advertisement messages. This helps hosts on a network discover routers and configure their default gateways. This is particularly important for IPv6 networks. Next is Path MTU discovery. MTU stands for Maximum Transmission Unit. ICMP can be used to discover the maximum transmission unit along a path between two devices. This helps avoid packet fragmentation and ensures efficient data transmission. Next is redirect messages. ICMP redirect messages inform a host that a better route to a particular destination is available through a different gateway, that is a router. This helps optimize the paths taken by network traffic. Next is time exceeded messages. When a packet's TTL value, that is time to live value, reaches zero, or a fragment of a packet fails to reach its destination within a certain time, ICMP time exceeded messages are generated. These messages help identify routing loops or packet fragmentation issues. Next is echo request and reply, that is ping. ICMP includes echo request and echo reply messages, which are commonly used for network testing and troubleshooting. The ping utility sends echo request messages to a destination host, and the host responds with echo reply messages if it is reachable. This is a widely used tool to check network connectivity. Next is destination unreachable messages. These ICMP messages inform the sender that the destination network or host is unreachable due to various reasons such as network congestion, no route to the destination, or a specific port being unreachable. Next one is parameter problem messages. These ICMP messages are sent when a router encounters an issue with the header of an IP packet, such as incorrect options or header length. These messages help diagnose and correct packet header errors. Next one is source quench messages. ICMP source quench messages are used to request the sender to reduce the rate of packet transmission to prevent network congestion. So, in summary, ICMP is an integral part of the internet and is crucial for network diagnostics, error reporting, and overall network health monitoring. While it plays a critical role in network troubleshooting and management, it is essential to use ICMP responsibly to avoid network congestion and potential security issues. Let's go to the next question. What is NAT and why is it used? NAT stands for Network Address Translation. NAT is a networking technique used to modify network address information in packet headers while in transit. NAT is typically implemented on a router or firewall device and serves several important purposes in modern networking. Let's see some of them. First is conservation of IP addresses. NAT allows multiple devices within a private network to share a single public address when communicating with external networks like the internet. This conserves the limited pool of public IP addresses, which are a finite and valuable resource. Next is address hiding. NAT masks the internal private IP addresses of devices within a local network from external networks. When devices in the local network communicate with external servers or devices, their private IP addresses are replaced with the router's public IP address. This adds a layer of security by hiding the internal network structure. Next is IP address reuse. RFC 1918 specifies private IP address ranges. These are reserved for use within private networks. For example, 192.168.xx or 10.x.x or 172.16.x.x. These are private addresses. NAT allows these private addresses to be reused across different private networks as they do not conflict with each other or with public IP address. Next is PAT, that is port address translation. A specific form of NAT called port address translation allows multiple devices within a private network to share a single public IP address by using different source port numbers for each connection. This enables many devices to access external resources simultaneously through a single public IP address. Next is IPv4 to IPv6 transition. NAT can help in the transition from IPv4 to IPv6 by allowing IPv6 enabled devices to access IPv4 resources and vice versa. This is known as NAT64 and facilitates the coexistence of both IP versions during the migration. Next is security. NAT provides a level of security by acting as a barrier between the private network and external networks. It prevents uncalled inbound traffic from reaching devices in the private network, enhancing network security. However, it should not be solely relied upon for security purposes. Next is load balancing. In some cases, NAT can be used for load balancing purposes. Multiple servers in a private network can share a single public IP address, and incoming traffic can be distributed among them based on specific criteria, like, for example, port numbers. Next is simplified network management. NAT simplifies network management. NAT allows devices within a private network to use private IP addresses without needing coordination with external entities for address assignments. This reduces the administrative burden associated with IP address allocation. So, in summary, NAT, that is Network Address Translation, is a critical networking technique used to conserve public IP addresses, enhance security, and enable the coexistence of private and public networks. It is widely employed in home networks and corporate environments to facilitate communication between devices within a private network and external networks like the internet, while providing a level of address and security management. Okay, guys, that's it for today. There are many other topics to be covered under networking. I will see you in another video where we discuss more about networking. If you like today's video, please don't forget to like, subscribe, and share our videos. I will see you in another video. Until then, bye bye.